in principle, in the second part of the lecture, here, I will save you and me the brief review of elementary methods to solve ordinary differential equations. Okay, you can find on my notes 1 page and a half of simple methods to solve ordinary differential equations, something like, I don't know, separation of variables or substitution, all these things. These are methods which in principle you are supposed to know from your previous studies, I guess. Huh? So I will skip this. In any case, they are on this page, 1 page and a half. Instead, so they are in this 1 page and a half. What I want to say, you can have, you can read them. If you don't understand something, please send me an email and ask me. Instead, what I would like to talk about now is the problem of stability. Which is going to be some important problem, not only for today, but also for next week, for the lecture next week. First lecture next week, possibly only the first one. So stability is basically related, if you want to connect it, to some kind of stability and of a qualitative analysis of the solution of some equation. Solution some differential equation. So suppose that you have a some differential equation that you were able to write in a very nice form, but you are not able to solve exactly. So imagine that you have done all the tricks that we have described to write some simple differential equation. Suppose that you are not able to solve then this equation. In any case, there are still some qualitative analysis that you can do on top of this equation to understand some features of the solution of the equation. For example, suppose that you have some autonomous ordinary differential equation. So you have an autonomous ODE. So what does it mean that an ODE is autonomous? Do you remember? So what's the first order? Sorry, first order ordinary differential equation. It's a differential equation where appears just the first derivative of the field. So imagine that the field is u, the variable is u. So you will have u prime. So it's what does it mean that this is an autonomous ODE? It is going to be a function of what?
U.
And then? No.
Time.
No, the autonomous an autonomous ODE is is actually an equation which does not depend on the independent fundamental variable, but just depend on the field. So, for example, if I have an equation which is like this one, this is a first order differential equation for u, for the field u. U is a function of t, but since in this differential equation you have no t, so t does not appear explicitly, t appears only as the derivative of u. Okay, but then you do not have an explicit dependence on t. Then these kind of equations are what they are called autonomous differential equation, ordinary differential equation. Now this kind of equation is relatively simple to solve, at least to write down the attempt of the solution. In principle, what I can do is to try to solve this differential equation with separation of variables. So what I'm doing is to try to look the integral of 1 over f of u in the u, and this should be equal to the integral of the t between 0 and t, which basically means t plus some constant. Fair enough. Nobody tells me that I'm always able to solve this integral, to find this integral. Okay? There are situations in which I cannot find this integral. Basically, there are also situations in which finding these integrals, it's possible to find the integral, but the integral is extremely difficult to find. Okay? So you do not want to bother in looking for an exact solution, but rather what you really want to do is to have an idea of how the solution looks like. So what are the most important features of the solution U? Okay? For example, one of the things that you can do without solving the ordinary differential equation, so without solving this equation, one of the things that you can do is to determine the equilibria of your problem. Well, actually, not only equilibrium, you can also determine something which is the dynamics close or near equilibrium. Okay, so these two things are two things that are relatively simple to do, even if you are not able to solve directly the differential equation which is written here. So let's see what this implies. How do we determine the equilibrium? We have done this before for the logistic model. Do you remember how do we determine the equilibria of the logistic equation? Let me remind you, the logistic equation was looking something like this. And you remember, we say that the equilibria of this model were capital P equal to 0 and the capital P equal to 1. So the equilibria of first order differential equation are found putting to 0 the right hand side. So putting to 0 the derivative of the field, the derivative of the function, we put to 0 this thing here. And what I have to do is to solve the right hand side equal to 0. So in the case of a differential equation which is u prime equal to f of u, this means that the equilibria are determined by f of u equal to 0. So what I have to do is, in order to find the equilibria of this model, is to find all the points u star such that f of u star is equal to 0. Let me give you a very simple graphical example. Okay, so suppose that I have some so this is a plot of u prime as a function of u. Now, u prime is by definition given by my differential equation, so it's given by this equation here. U prime is some f of u, some function of u. So suppose that my function of u is something which is doing like this. Wow. Okay, so this is the plot of f of u. Now the equilibria are given by those points of f of u, which for which well actually that cross this axis here. So the equilibria are going to be this point here, this point here, and this point here, because these points are those points for which f of u is equal to 0. Okay? So let me give names. Let me call these points is the point A, this other point is the point B, and this third point is the point C. Then the equilibria are going to be some u star, which are given by A, by B, or by C. Well, allows me to use capital letter. If you want, I can write with well, let's write with small letter. I don't want to confuse. Since these are some coordinates, A, B, and C. Okay. Now, what we can do is try to understand what is the flow of the field U as time goes by. So what's the behavior of the derivative of U as time goes by? Okay, this is useful to classify the equilibrium. For example, let's see. What I can do is, for example, this here, the flow is going in this direction. In this zone here, the flow is going in this other direction. Why? Because basically in this region here, u prime is positive. Okay, so the flow of u is going in this direction. In this region here, u prime is negative. Remember that u prime is equal to f of u. So in this region here, u prime is negative. So the flow of u is going on the other side. So what happens here? Here? No, in this region, how is the flow? No, the flow is still negative because this region corresponds to u prime negative. I'm still in the region where u prime is negative. So the flow is still in this direction. What happens in this region here? Here is positive because u prime, which goes like f of u, in this region is positive. So the flow is going in this direction. Also here is going in this direction. What happens here?
Positive.
That's still positive. Because also in this region, u prime is positive, so the flow of u is going in the positive direction. Okay, so this allows me, if you are attentive enough, if you are paying attention enough, that there are three possible behavior of these equilibrium points, of this equilibria. One behavior is the behavior of the point A. The point A, if you see, there is the flow of solution U is going always in the direction of the point A. Okay, so the point A is what is called an attractor. It's attracting the solutions. That's why it's an attractor. The point B has the opposite situation. So the point B is here, and the flow is always going away from the point B. So with the great effort of fantasy, B is called a repeller, because it's repelling the solutions. The other possibility is points like the point C, where on one side the flow is going toward the direction C, and on the other side the flow is going away from the point C. So the point C is called an hyperbolic equilibrium. Now, the point which are attractors, so basically, parentheses, these lines here, which are telling you how the flow of the field, how the flow of the function U is behaving, where it's going in the flow. These are called phase lines. Now, what are the interesting things of attractors, repellers, and hyperbolic equilibrium, as I was telling you before, basically? So, an attractor are locally, asymptotically stable points. So basically this means that if I'm taking a system and I'm starting with some initial data which are close to the point, to the attractor, to the point A, in this case, as t goes to infinity, I will reach the equilibrium. I will reach the point A. That's why actually I have these arrows which are pointing toward A. So I'm taking a system, I'm going, I'm starting with some conditions which are not in the equilibrium, but are close to the equilibrium, so in a region close to the equilibrium. The solution, the dynamics of the system is such that I will approach in an infinite amount of time, as t goes to infinity, to the equilibrium. That's actually, for example, what happens in the case of the logistic model, the logistic equations. If you remember, we were starting with some solution, wherever it is solution, and then for t that is going to infinity, I was approaching the equilibrium p equal to 1. So p equal to 1, in that case, for the logistic equation, was an attractor, is an attractor. Repellers and hyperbolic points, hyperbolic equilibria, instead are unstable. So these are stable, instead repellers. And hyperbolic points are unstable. Unstable. This basically means the exactly the reverse of the definition of these stable points, right? So if I'm starting in a region which is close by to the equilibrium point, so to the repeller or to the hyperbolic equilibrium, the dynamics of the system is taking the system away from the equilibrium. So that's why I have these arrows close to the point B, which are going in the opposite direction. So if I'm starting with some conditions which are close by to B, the system will evolve away from the equilibrium B. And that's actually the same that happens to the point C. For this reason, repellers and hyperbolic equilibria are unstable points, while attractors are stable points. In particular, note that I say that attractors are locally asymptotically stable points. Actually, an attractor can be also some globally asymptotically stable point. This happens if for any perturbation that I'm taking, the system is approaching to the attractor. So I'm starting from any point which is not supposed to be very, very close to the attractor, can be wherever you want in your phase space, but for t that is going to infinity, the system, the dynamic of the system is always going in the direction of reaching the equilibrium A, reaching the attractor. So in this case, the attractor will be some globally asymptotically stable point. Let me write down. If the equilibrium is stable for any perturbation, then it's a globally asymptotically stable point. Now, there is some nice characterization. If you do not want to remember this thing of direction of the flow, there is some nice characterization that you can give to some equilibria, especially to attractors and to repellers. So, for example, in the case of the attractor, so in the case of the point A of our figure, we can see that the derivative of f with respect to u in A, how is this derivative in this point A? So here,
0.
No. This is not 0. It's negative. It's not. It's negative.
The second.
So in the derivative of f in the point in the attractor is negative. The derivative of f in the repeller instead is positive. Now, whenever you have a derivative which is less than 0 in equilibrium, you are sure that this is an attractor. And whenever you have a derivative of f in a repeller, which is, whenever you have the derivative of f which is greater than 0 in a point, that is an equilibrium point, you are sure that that equilibrium point is a repeller. You cannot say, if you have f prime of an equilibrium point equal to 0, you cannot say for sure that that is an hyperbolic equilibrium. So you cannot say that this is surely an hyperbolic equilibrium, because basically you can have a flex. So if you have some situation like this one, oops. Okay, you will have here the derivative is equal to 0, but in any case, this one is going to be this is a repeller point, because this is going in this direction, and here the flow is going in this direction. So this would be a repeller point. Sorry, the other way around, because this is going to be an attractor, because here is positive. Sorry, here is positive, so the flow is going in this direction. Here is negative, so the flow is going in this direction. So this is going to be an attractor, even if f prime in this point is equal to 0, because here there is a flex. So whenever f prime is equal to 0, I cannot assure that this is an hyperbolic point, or an attractor, or a repeller. Okay, but what I can say for sure is that if f prime in the equilibrium point is less than 0, then it's an attractor. If f prime in the equilibrium is greater than 0, then that's a repeller. This is something which you can see also from the analytical point of view. Indeed, we will see now in a moment. So suppose that I'm starting with my equation u prime, my differential equation u prime equal to f of u, and let me suppose that this is to some equilibrium point. In some equilibrium state. Then let me take a small perturbation from this equilibrium state. So the small perturbation, I will call the small perturbation capital U of t. So capital U of t is a small perturbation. Perturbation around the equilibrium U star. So basically this means that I will consider my field, my function u, to be equal to some u star plus the small perturbation capital U of t. Okay. Now u prime, what's u prime? U prime I can differentiate, I can derive left hand side and right hand side of this equation. U star is constant, so the derivative of u star is going to be 0. The derivative of the right hand side is just capital U prime. On the other side, I know that u prime satisfies my differential equation. So I know that u prime from here is equal to f of u from here. This is equal to f of u. But again, this function f is a function of u. U can be separated, can be expanded around the equilibrium u star. So this can be written as a f of u star plus the perturbation capital U, just using this equivalence. So now what I have to do, what I want to do is to expand, Taylor expand this function around u star, around the point u star. So what I will have, it's f in u star plus the derivative of f in u star times u minus u star. U minus u star is capital U, plus 1/2 of the second derivative of f evaluated in u star by order higher order in u squared that I don't care, terms that I want to discard. Okay. So I'm now in the position of saying that u prime, capital U prime, is equal to f of u star plus f prime in u star times u. Star up and down is just a mistake, okay? It's not any meaning. So in this case, okay. What do I know here? So what about fu star? What's fu star? Any suggestion?
It's equal to u the first equation u prime equal to f of u.
Yeah, but now I have f of u star.
Is equal to 0?
Why?
Because u star is an equilibrium or not?
Yes, u star is an equilibrium. So f of u star is by definition equal to 0. U star is exactly the point in which f is 0. So this is equal to 0. So what does it mean? This equation reduces to u prime, capital U prime, equal to some f prime of u star times u. This is a very simple differential equation in capital U. Do you know what is the solution of this equation? Capital U equal to what? What? No, I'm looking to capital U. So U prime, now since fu star is equal to 0, this equation is just this. But this is a differential equation in capital U. Okay? I can solve this equation. This is very basic with the separation of variables. And the solution of this equation is something, which is going like this. Times t. So the solution of this equation is the exponential. Right? Try to do the derivative. The derivative of this is f u prime star times the exponential, which is exactly what's written on the right hand side. Okay? But now observe something which is very interesting. I still didn't say anything about f prime. So what can I say now looking at the sign of f prime in the equilibrium? If f prime is less than 0, suppose it's a constant less than 0, here I would have an exponential of minus some positive constant now. Sorry, let me use some other alpha. Minus alpha times t. Which basically means that for t that is going to infinity, this guy is going to 0. Right? So basically means that as t goes to infinity, the perturbation is going to 0. So means that u, the solution small u, as t goes to infinity, is approaching the equilibrium. which is basically what we have said when we observed that if the derivative of f in the equilibrium point is less than 0, then that point, that equilibrium point, is an attractor. Okay? Attractor because even if I'm starting from some point which is close by the equilibrium, then the dynamic of the system is going toward the equilibrium point, toward the attractor. On the other way, if f prime of u star is greater than 0, then it means that I can write the solution capital U as something which is proportional to the exponential of some positive numbers, let me call beta, times t. What does it mean? That for t that goes to infinity, this terms goes to infinity, explodes. Correct? But this situation here, remember, corresponds to f prime of u star greater than 0, which basically in our plot corresponds to this thing. And indeed, we say that f prime greater than 0 in equilibrium point characterize what? A repeller. In fact, if I'm starting from a small perturbation from a repeller, the dynamics of the system is going somewhere else, but surely not in the point given by the repeller. No. It's clear? No, it's not clear? Clear, not clear?
The function u, it's more versus capital U.
Capital U is a perturbation. So imagine that I'm starting from u, from small u. Okay? Small u is given by a component. Oh, disappeared. I don't know why. Small u, it's a first component, which is the equilibrium, and the second component, which is the small perturbation. Okay, so this is my solution u.
Yes.
I want to see where small u is going.
But when we have beta, the functions goes to the perturbation.
No.
It's not okay.
This is exactly the perturbation. So this tells me when you have beta, so when you have the f prime of u star greater than 0, this means that u, capital U, is becoming very large. If capital U is becoming very large with the time, this means that the limit for t that goes to infinity of u of t is going to be equal to the limit for t that's going to infinity of u star plus u of t, but that is going to go, who knows? Well, infinity. If you write it this way, it is going to infinity. Instead, in this first case, in this other case, what I have is limit for t that's going to infinity of ut is equal to the limit for t that's going to infinity of u star plus u. And what is this? No?
U star.
That's u star. So in one case, I'm going outside, far away from u star. In the other case, I'm going toward u star. That's actually u star here, in this case, is an attractor, and this one is a repeller. From home. Is it working? I hope yes.
Yes.
Great, thank you. So now let's see some application again to the logistic model. I mean, the logistic model is something that appears many times in applied mathematics and in many contexts. So It's like the heat equation. Actually, there are 3 or 4 equations that are appearing always with some modification. So let's consider the example of logistic equation, logistic model with the harvesting term. Harvesting term. This is an harvesting. So logistic model, if you remember, it's the P in the T equal to R times P that multiplies 1 minus P over K. This is the logistic model. The only thing that now I'm adding is an extra constant term, oops, capital H. An extra term, which is this capital H, which has the dimension of what? What are the dimensions of capital H? No. L here does not appear. No. Test dimensions. No. It must have the same dimensions of the other quantities in the equation. Otherwise, the equation would not be well written. So it must have the same dimension, for example, of this term here. So the dimension of H, it's population over time. Okay? Because this term here has the dimension of population over time. This term here is the dimension population over time. So also H must have the same dimension of population over time. What is the meaning of this term? What do you imagine is this term? So suppose that this logistic equation is describing the evolution of the population of pigeons. You have an area with pigeons, population of pigeons. The first term tells you, okay, is the rate of growth of the population. This tells you the pigeons that are born or die in the region. These terms here, we say that it's a competition terms of pigeons that are eating the same food, so there is no food for everybody, and this is the term that is modeling this fact. What do you think this is telling you? What's this H? So actually, the name probably could tell you something. It's an harvesting term. So basically, it could be any kind of cause, external cause, hunting, which are taking out a certain number of pigeons from my population. So imagine this as hunting term. If these are pigeons, imagine that H is the hunting term. So
it's a closed system. Or we said it's a closed system, nothing and
no pigeons enter, no pigeons go out, but I can have an hunter in the system.
It's always a closed system.
It's always a closed system. If it were not a closed system, I would have here extra terms coming from the flow of pigeons from outside or flow of pigeon from inside to outside. Since I want a closed system, so I'm just adding this term minus H for saying that the number of population is decreased by this rate H because of something, because of hunting, because of a disease. Imagine that there is a disease of pigeons which are killing H pigeons. So a certain number of pigeons in a certain amount of time. That's the meaning of capital H. So now what we are doing is to do what we have done at the beginning of our lecture, to pass to dimensionless variables. So I will define, this time I'm not calling it capital P, I'm calling it U, just to confuse the ideas more. So my dimensionless variable, if you remember, a dimensionless variable for the population was population divided by the carrying constant, K. So this is dimensionless. And another dimensionless parameter, the dimensionless time, let me call it this way, was given by what? Do you remember? What was the other dimensionless parameter? Tau? Don't remember. No? So, no, you cannot see. It's T times R. So T times R is the other dimensionless parameter of the problem. If I'm using these two parameters, I can rewrite the logistic equations with the harvesting term in this way. This becomes the U in the tau equal to U times 1 minus U minus, let me call small h. This small h is equal to capital H divided by R times K. Sorry, R times K. What's the dimension of small h? What's the dimension of this thing?
T.
No. Help from home. What's the dimension of small h?
Sorry, small h is equal to capital H.
No, capital H divided by R times K. But you can see also from the equation. It's very good.
Same
It's
as capital H.
dimensionless. It's dimensionless. Also because this thing is dimensionless. U and tau are by definition dimensionless. And also these things are dimensionless because U is by definition dimensionless. By construction, sorry, not definition, by construction.
Sir, hello.
Yeah?
Here R is dimensionless and K is dimensionless, right?
No, R has the dimension of R is time minus 1. And
okay.
K, the dimension of K is population. Let me call P, I mean population, number of people, of pigeons, whatever, of mosquitoes. Okay?
Yeah.
Does it work?
Okay.
Now, how can I find the equilibria of this model? The equilibria of this model are the solutions of the equations U times 1 minus U minus H equal to 0. Are the solution of this equation here equal to 0. Now this is a trivial equation of second order in U, so you can find easily the solutions. U star, these are going to be 1 plus minus the square root of 1 minus 4 small h divided by 2. And now there is something nice that happens. What happens if h is larger than 1/4? Don't look at me, look at the square root. You have no solution. So for h larger than 1/4, since you have no solution, this means that you have no equilibrium. So I can have equilibrium only if h is between 0 and 1/4. Okay? And I will have two equilibria, actually. One equilibrium is corresponds to the sign plus, and the other equilibrium corresponds to the sign minus, right? So two equilibria. 1 plus square root of 1 minus 4h divided by 2, and 1 minus square root of 1 minus 4h divided by 2. Okay? Now, what I want to do is try to study this equilibrium when h changes. So a nice thing to do would be to build up a diagram of U star of the equilibrium points versus the parameter h that I'm changing. So I want to see what happens to the equilibria when I'm changing the harvesting parameter. This thing here, well, basically you should plot this equation. If you're plotting this equation, what you will find is something like, well, something like this. So this point, let me call this point B, this is the point that corresponds to h equal to small h equal to 1/4. So if h is larger than 1/4, h larger than 1/4, I'm here and I have no solution, no equilibrium. That corresponds to this thing written here. Okay? When h is smaller than 1/4, so between 0 and 1/4, then suppose that, for example, I'm considering this h here, then, well, my drawing is not very good, but I have 1 point here and 1 point here. So I have two equilibriums, one here and one here. This is for h between 0 and 1/4. So this diagram is what is called the bifurcation diagram. And the point B, corresponding to h equal to 1/4, is what's called the bifurcation point. So these 2 points, this and these, for each different small h, corresponds to a different equilibrium, correspond to 2 different equilibria between the growth rate of pigeons and harvesting. So this point U star, these 2 points here and here, will correspond to 2 different equilibria between the how much the population is growing and how much the population has been harvested. the point is there any equilibrium between these two which is favored by nature? So consider that all the points which are in this branch corresponds one point which is in this other branch, right? Because this is the branch corresponding to the plus sign, and this is the branch corresponding to the minus sign. They are symmetrics, yes, and then they just depend on small h. So if small h, for example, is 1/5, there will be 2 points, one in this branch and one in this other branch. If small h is equal to 1/8, there will be 2 points, one in this branch and one in this other branch. So my question now is try to understand if there is one of the two branches which is favored by nature for some reason. Then in order to do this, what I'm doing now is to write down my plot here of what? Of the differential equation. So of this. Here, let me plot u prime equal to f of u. F of u in this case is this thing here. This is some parabola which is going up and down, and with the version parabola which is going downwards. The parabola is going up and down as a function of small h. So if small h is less than 1/4, what you will have is something like this. This is u prime in terms of u. This is f of u. That's exactly the same analysis that we have done here. The same analysis. But here we have just drawn some f of u. We invented some f of u. Instead, this is a very well specific case of a very well formulated problem. So my f of u in this case is u times 1 minus u minus h. I draw in this way because I'm supposing already that h is between 0 and 1/4. If h is larger than 1/4, this thing is going down the axis u. So I would have something like this. This would be the case, h larger than 1/4. But for the moment, forget about this case. All right. So you remember what are the equilibria for this problem? The equilibria are the point here and this other point there. Great. This point here corresponds to the equilibria. Let me call u minus. This is u plus. So this point here corresponds to the u minus. This one corresponds to u plus. Now, what is u minus? Is an attractor or a repeller? That's a repeller, because here the flow of u is in this direction, here is in this direction, here in this direction, here is in this direction. What about u plus? Is an attractor or a repeller?
Attractor.
That's an attractor. Very good. So what we have seen from here is that u minus is a repeller. U plus is an attractor. So what does this tells me? Even if I have two equilibria, u plus and u minus, What do you think the nature is favoring, U plus or U minus? The nature is gonna prefer U plus because U plus is the attractor. So even if I have these two equilibrium points between the growth of the population and the harvesting of the population, nature is gonna prefer the U plus, the attractor between the two, which basically means that nature will gonna prefer the this branch of the bifurcation diagram. Although from the mathematical point of view, also the lower branch will correspond to some equilibrium, but these equilibrium of the lower branch are gonna be repellers. And I think that this is the last thing that I would like to tell you today. But before finishing, I just would like to give you a couple of exercise with which that you can do to train a bit the kind of problems that you can find in this course, and it's going to be also the kind of problems that eventually you can find in the exam. So the first problem is the following one. Suppose that I'm revisiting the blast wave problem that we have seen yesterday. So suppose, assume that there is a relation between t time r, which is the distance of the shock wave, rho, which is the density of the initial density of the air outside, E, which is the energy of the explosion. Yesterday we have considered also just this case, but now suppose that this thing is depending also on P, where P is the environment pressure, ambient pressure. So suppose that there is a relation between these 5 quantities. What I want you to do is to find the dimensionless parameters pi's, and try to see how does R vary with T. And then compare with the problem that we have solved yesterday about the blast wave. Then the second problem. In the second problem, we're doing some test for cars, and cars are driven at a velocity v, which is constant, on a highway, flat street, so you don't have any other component which is coming from the fact that the street is not flat, and so forth and so on. So assume that the force of propulsion of the car, which I will call capital F, suppose that capital F is affected by the velocity v by the rate c at which fuel is burnt, and I will tell you that the dimension of this c is equal to a volume, so L cube times t minus 1. And then, so F is affected by the velocity, by this rate of consumption of the fuel C, and then is affected by the amount K of energy per kilo of fuel. And I can also tell you that the dimension of this capital K is equal to m times L minus 1 times T minus 2. So the problem is determine F. It's all. Questions or comments or ideas or desires, wishes? No wishes against my person. The only wish is that this lecture is over. All right, guys, then the lecture is over. If you have any problem, let me know. Well, drop me an email, send me an email, and we'll be very happy to answer to your doubts and questions. Okay? It's over. Thank you. See you next week. Bye.
Thank you. Bye.
Cheers.
Bye, Professor.
Bye.
Bye.
Bye, Sir.
Bye, Professor.
You.